Good day, uni students. I'm Norman Wildberger from the University of New South Wales. This is the second video in a series where I'm trying to explain mathematical terminology to people from a non-English speaking background who are entering university and are going to be doing some mathematics at the university level. So I'm going to go through different areas of mathematics, and we're going to review the essential terminology, the language that we need to understand the mathematical concepts suitable for first year university mathematics. So the idea is that I'm going to explain things very quickly and concisely. I'm not going to write down a lot of definitions. I'm just going to explain things verbally, and you're going to see the words on the screen. So you'll be familiar with the words and how they're used. Okay. So in mathematics, of course, language is very important. The meanings of the words you have to understand before you can appreciate the theories that are built up from those concepts. In today's talk, we're going to talk about geometry, okay, and terminology used in geometry. So let's go back to the most basic fundamental geometry, planar Euclidean geometry. Euclidean referring to Euclid, the ancient Greek mathematician who wrote the famous book, The Elements, upon which most of modern geometry is based. And planar referring to the two-dimensional aspect. We're just working on a plane. Familiar concepts, a point, a line. These arrows are to remind you that a line extends indefinitely in both directions. When we want to talk about a finite piece of a line, something like this that has a definite endpoint here and an endpoint here, we refer to that as a line segment. Okay, some basic notions having to do with lines. Here are parallel lines, meaning that they are oriented in the same direction, or Euclid would have said these are lines which do not meet, even if you extend them indefinitely. So complementary to the idea of parallel lines is the idea of perpendicular lines. This line and this line are called perpendicular, denoted by this little square that we see at the intersection. And we often refer to this as a right angle, or in degrees, 90 degrees. In the radian system, we would say this is pi by 2. But it's probably most naturally described as being a quarter turn. So those are all ways of representing the angular separation between perpendicular lines. And here's another important object from Euclidean geometry, a circle with some associated words, the center of the circle. And I remind you, the center of a circle. And I point out that there are two different spellings of center. So kind of American spelling ending ER, or British, Australian spelling ending RE. Both are fine. Some other concepts, the concept of a radius. It's a line segment from the center to the circumference, which is the outside of the circle. Circumference. A diameter refers to a line segment that goes from one part of the circle to another part of the circle and goes through the center. A chord is a line segment that goes from the circle to the circle, but which doesn't go through the center. And a tangent refers to a line which touches the circle at exactly one point. Now I have to point out a little bit of ambiguity here, right, that can be confusing. The terms radius, diameter, and circumference both refer to an object and sometimes to its length. So sometimes when we refer to the radius, we're actually talking about that line segment. And other times we use the same word to mean the length of that line segment. So it can be a little bit confusing. You have to be aware that the same word is being used in two somewhat different ways here. Similarly, when we refer to a diameter, we are referring to sometimes a line segment that passes through the center, or the length of a diameter is also called the diameter of a circle. And similarly, when we talk about the circumference, sometimes we're talking about the actual object, the actual circle, the outside of the circle. And sometimes we're referring to the length of that circumference. So I want to keep that in mind, that there's a bit of ambiguity with respect to those terms. Now, so these are some fundamental concepts coming from Euclidean planar geometry. Let's introduce some basic shapes from planar geometry. First of all, a rectangle, which is something created from four line segments which are all perpendicular. This perpendicular to that, this perpendicular to that, this perpendicular to that, and this perpendicular to that. So we have four right angles, or four quarter turns there. In particular, that means that this side and this side have equal size, or the ancient Greeks would have said that these two segments are actually equal. And similarly, these two opposite sides are equal. A square is a particular type of rectangle that has the property that each of the four sides are equal. A parallelogram is a kind of generalization of a rectangle where the opposite sides are parallel. So these two sides are parallel and these two sides are parallel. That's called a parallelogram. And a particular type of parallelogram, different from a rectangle, is a rhombus. Well, that's a parallelogram that has the additional property that each of the four sides are equal. So it's like a square, but a square that has been sort of squished. Right? Four equal sides, but not necessarily at right angles. This is the shape of a kite that you fly in the air. All right, so all of these have four sides and four vertices. If we have just three vertices, we have, of course, a triangle. So a triangle refers to a figure with three vertices. Here are the vertices. Sometimes we want to refer to the three sides as being a different kind of object. So sometimes we also may talk about a trilateral, referring to the three sides of the object rather than the three vertices. But these are just subtly different points of view on the same kind of object. The difference between emphasizing vertices and sides is a little bit clearer when we go to four vertices or sides. If we have four vertices and we think about the object formed from those vertices, we call that a quadrangle. Generalizing a triangle. Tri is root meaning three, and quad is a root word meaning four. The corresponding word for a trilateral with four sides is quadrilateral. So when we talk about a quadrangle, generally we're thinking about an object like this with four vertices. When we're thinking about a quadrilateral, we're thinking of an object like this with four sides. And you might think that they're pretty well the same, and often they are used interchangeably, but in projective geometry there is an important difference between them. So triangles, quadrangles or quadrilaterals, and sort of special types of quadrilaterals or quadrangles. Let's have a further look at triangles. So there are some special types of triangles. The right triangle which is a triangle that has a right angle, or 90 degrees, or a quarter turn between two of its sides. There is an equilateral triangle where all three sides are equal sides. An isosceles triangle is a triangle which has two equal sides. In this case, this one and this one. The third side does not have to be equal to those ones. If it was, then we would have an equilateral triangle. An isosceles triangle can also be described by having equal angles here. Or, if you've learned some rational trigonometry, equal spreads. So, for example, in the case of an equilateral triangle, all these three spreads are equal. They all turn out to be a spread of 3/4. In terms of angles, they're all angles of 60 degrees, or pi/3. Now, triangle geometry is actually a very rich subject, and there are many additional interesting points associated to a triangle. It's important that you're aware of at least 3 or 4 important ones. So, one of these points is called the centroid, and that's obtained by taking the 3 medians of a triangle. What is a median? Well, if we take a side, say the side from A to B, then the point which is halfway between A and B is called a midpoint. So that's a midpoint, there's a midpoint, there's a midpoint. A triangle has 3 midpoints. And if we join the vertices of the triangle to the opposite midpoints, then that line is called a median. So here are the 3 medians of this triangle ABC. And the 3 medians meet, or intersect, in the point called the centroid. This is also the point of balance of the triangle. If you actually cut out this triangle with a piece of wood, this would be the place we'd have to choose to balance that triangle on your finger. Another important point is the orthocenter, which is the place where the 3 altitudes of the triangle meet. An altitude is a line from a vertex which is perpendicular to the opposite side. So this line right here is the altitude from the point B to the side AC. This side and this line are perpendicular. There are 3 such altitudes, and then it's a beautiful fact that those 3 altitudes meet at a point, just the same way that the 3 medians meet over here. And this point is called the orthocenter of the triangle. There's another important point called the circumcenter of the triangle, and that's obtained by taking the 3 perpendicular bisectors of the sides. So here's a triangle ABC, and here we see the 3 midpoints, same points as we had over here, halfway along each side. And now from any one of these midpoints, if we draw a line which is perpendicular to the actual side that the midpoint is on, so this line is perpendicular to this one, this is called a perpendicular bisector of that side. And there are 3 perpendicular bisectors, and they meet at a point called the circumcenter of the triangle. And it's not too hard to see that that's the center of the circle which passes through the 3 points of the triangle. Every triangle has a unique circle that passes through the 3 points. That's called the circumcircle of the triangle. All right, so these are 3 important points from triangle geometry: the centroid, the orthocenter, and the circumcenter. And I hope that you've heard of the fact that those 3 points are always collinear. They lie on a line called the Euler line of any triangle. If you don't know that, you might like to experiment and check that's actually true. It's a beautiful fact that goes back to the great Swiss mathematician Leonhard Euler in the middle of the 18th century, the 1750s. There's a bit of triangle geometry. So we've talked about triangles, which have 3 vertices, and quadrangles, which have 4 vertices. We can go higher, talk about, say, a pentagon, which has 5 vertices, or, if you like, 5 sides. Then something with 6 sides, or 6 vertices, is called a hexagon. And this is an example of a special kind of hexagon, one called the regular hexagon, which has the property that all of the 6 sides are exactly equal, and all of these angles or spreads are all also equal. So it's a very symmetrical hexagon. So these are examples of polygons, or sometimes called n-gons. And there are higher ones too that have names. If you have 7 sides or 7 vertices, sometimes called a heptagon. With 8 sides, we get an octagon. That's like a stop sign. 10 sides, we refer to a decagon. The deca referring to, again, 10, like decade or decathlon. When we're talking about general polygons, or n-gons, then there's an interesting and important idea of convex or non-convex. So here is a polygon, a general polygon, which happens to have 6 sides, so it's actually a hexagon. But it has the property that it's convex. And what that means is that if we choose any 2 points inside the hexagon, then the line segment between those points is also inside the polygon. That's called convex. Here is a non-convex polygon, sometimes called a concave polygon. So concave is the opposite of convex. And this means that it's not always true that if you take 2 points inside, in other words, in the interior, this is the inside or the interior of the polygon. If you take any 2 points, then it's not always true that the line segment joining them is contained completely inside the polygon. That property is true for this polygon. No matter which 2 points you choose, the line segment's inside. Here it's sometimes true, but sometimes not true. So this is called a concave polygon or a non-convex polygon. Probably I prefer the word non-convex rather than concave. So I suggest you stick with that. Convex and non-convex. When we're talking about the interior of the polygon, that's this region here. Complementary to that is the exterior, the outside. All right, so exterior means outside, interior means inside. When we study geometry, we study not only objects, but we also study the motions of those objects, ways that we can move objects to create new objects. And the word that we use in mathematics for this kind of thing is sometimes we refer to motions, but sometimes we refer to transformations, and sometimes to mappings. So these are 3 words which are almost the same meaning. So for example, here is a triangle ABC, this one right here. And we can imagine taking that triangle and moving it in various ways. So one motion would be to move it like this down here, to translate. This is called a translation of the triangle. Another motion is a rotation. If we rotate it like this, we move the whole thing like this, that's a rotation about this center A. So rotation is like this, or maybe like this. That's also a transformation or a mapping. Another example of such a kind of transformation that we consider is a reflection. For example, if we take this triangle ABC and we reflect it about this line, that means we think of this as being a mirror and send this point to the point on the other side, which is equally spaced from the mirror. A sent to A, B sent to B, C sent to C. Then what happens is that the triangle is flipped over and reflected to get this triangle over here. So these are all particular kinds of transformations or mappings called isometries, or sometimes congruences. This means that they preserve segments or distances or lengths, or I prefer to think of in terms of quadrants, which is the square of the distance. So an isometry is a transformation that keeps the measurements the same. So this segment AC is the same as that segment AC. This segment AC is the same as that segment AC in terms of how big it is. AC here, the same as that there. So those kinds of transformations are called isometries or congruences, or another word that's sometimes used is rigid motions. Rigid motion is another name for isometries or congruences. There's another kind of isometry or congruence which is called a glide reflection, which is the composition of a translation and a reflection. What does composition mean? That's an important operation. It's when you perform one operation and then you perform a second operation. We say we compose two operations. So for example, if we start with this house and imagine doing two things to it. Imagine first translating it so that it's now over here, and then reflecting in this line. Okay? So imagine the house first moving over there, and then we're reflecting it in this line. So that's the composition of our translation and a reflection. And that net effect, that combined transformation, is called a glide reflection. Taking the house here, twisting it, and translating it to get the house over here. So these are important kinds of isometries or congruences or rigid motions that we study in planar Euclidean geometry. Okay, so closely associated to the idea of a congruence or an isometry is the idea of congruent figures. So a figure is a very general word that applies to any configuration in the plane. It's like a picture, a mathematical picture. We would call that a figure. And we say we have congruent figures, like this one and this one, when they are connected by an isometry or a congruence. So this rectangle, ABCD, and this rectangle, FGHE, look the same, except that one is moved, translated, and rotated, but the shapes are the same. They are the same size, and they have the same shape. They're just in different positions. So we say these are congruent figures. In the world of geometry, this is like equality of some kind. And this is the symbol that we would often use for that. So one way of describing this rectangle is to write ABCD with a line over it. That's what I prefer. So this means that this rectangle ABCD and this rectangle FGHE are congruent. And it means actually something a little bit stronger. It means that the congruence is such that the point A corresponds or is matched up with the point F, B is matched up with G, C is matched up with H, and D is matched up with E. So imagine A and F are sort of corresponding, B and G are corresponding, C and H are corresponding, and D and E are corresponding. Now sometimes people use different symbol or notation there. So another way of describing this rectangle or quadrilateral is to use a little square. Right. A, B, C, D is congruent to the rectangle F, G, H, E. Now, besides having congruent figures, we also have the idea of similar figures. That's when two figures look the same, but one is scaled down or up from the other. So they have the same shape, but not necessarily the same size. All right, so here, A, B, C, D, this rectangle, and this rectangle E, F, G, H have the same shape, but not the same size. And so we say that they are similar. Not congruent, they are similar. And we use a different equality. Instead of having a sort of like a half equal sign there, we have two wavy lines, meaning that they're somewhat a little bit less equal than these two are up here. But there's still a close connection between these two figures. And this kind of relation, when we're allowed to expand or contract, that's sometimes called a similarity. And we refer to a dilation. So for example, if we imagine just blowing up the plane by increasing the scale, like zooming in or zooming out, that's called a dilation, and we refer to that motion as a similarity. It's not a congruence, not an isometry, it's something a little bit different, a little bit weaker, called a similarity. So for example, if we consider this point as fixed and imagine expanding the entire plane centered at this point by a factor, say, of 3, then this little house here would get blown up to become this big house here. And so this is called the center of dilation. 3 is the factor of dilation. And this is a transformation that takes this figure to a similar figure, but not a congruent figure. So these are similar, but not congruent. All right, so now let's talk a little bit about three-dimensional geometry, where we have not just points and lines, but also planes. A plane in three-dimensional space. And generally, just as for a line, we imagine the plane extending in each of the 4 directions indefinitely if necessary. All right, then there are some new kinds of interesting objects in three-dimensional space that we can talk about. For example, a cube, which is the analog of a square. So a cube is a three-dimensional object which has equal faces. Each face is a square. You can see that there are 6 faces, 4 in the middle, 1 on top, 1 on the bottom. There are 8 vertices or corners, and there are 12 sides or edges. A generalization of a cube is a parallelepiped, which is the analog of a parallelogram in three-dimensional space. That's a rather long and complicated word, a parallelepiped. Here's an example of that. And so we're talking about something that's like a cube, except that the faces are not necessarily squares. They are just parallelograms. But this side and this side are parallel. In fact, this side and this side are also parallel, and so are these. So there's 4 parallel equal sides in that direction, 4 equal parallel sides in this direction, and 4 equal parallel sides in this direction. So there are each of these faces is a parallelogram. And here is a cylinder, which is what you get when you roll up a piece of paper. It has a circular base and a circular top. And another way of combining a circle and some lines is by creating a cone. So we have a circle here, and then above the circle a point, and then we connect the point with each point of the circle, and we get a cone, like an ice cream cone. Another kind of three-dimensional object is a prism, where we have a base, in this case some kind of pentagon, and above it is an equal congruent pentagon, exactly above it, and we have vertical lines that join corresponding points. That makes what's called a prism. And there's important formulas associated to these in terms of volumes. So the volume formula for a prism is the area of the base times the vertical height. While over here for a cone, the volume of a cone is 1/3 of the area of the base times the height. Again, the height meaning a vertical height. All right, some basic three-dimensional shapes and two important volume formulas. So we cannot leave three-dimensional geometry without mentioning the 5 Platonic solids. Very important historically and very beautiful objects in mathematics. Going back to the ancient Greeks, Plato was an important philosopher, writer, and friend of mathematics. These Platonic solids are also called the regular polyhedra. So a polyhedron is a three-dimensional analog of a polygon. It's a shape whose sides are all polygons. That's what a polyhedron is. And the plural of polyhedron is polyhedra. It's from the Latin. And there are 5 regular polyhedra. Regular in this case, it's the analog of a regular polygon, where each of the faces is a regular polygon, and each face looks exactly the same as every other face. There are 5 of them. The tetrahedron, which has 4 equilateral triangle faces. It has 4 vertices, and in fact 6 edges. There's the cube that we've already seen before, and there's an octahedron, which has 8 triangular faces. It's kind of a square equator, and then a pyramid on top of that square and a pyramid below the square, and the whole thing is completely symmetrical. And then in addition, there are these 2 very remarkable and beautiful mathematical objects called the icosahedron and the dodecahedron. The icosahedron is made out of equilateral triangles, okay? And there are 20 of them. And the dodecahedron is made out of regular pentagons, and there are 12 of them. So dodeca refers to 12. A dodecagon is a 12gon. Okay, these are very important, beautiful objects, so please make sure that you at least are familiar with the words, because they come up in a lot of situations historically especially. Now, no introduction to geometry would be complete without mentioning Cartesian geometry, which is a much more modern form of geometry introduced by René Descartes, a French 17th century mathematician. And the idea is to introduce coordinates and a coordinate framework with axes, and then to refer to points, lines, and other figures in terms of the x and y coordinates. All right, so the basic objects here are called the axes, the x-axis and the y-axis. So usually we have a little arrow there indicating the direction of increasing coordinate for the x. And we have equally spaced points, 0, 1, 2, 3, 4, and so on in that direction, and -1, -2, -3 in that direction there. And then in the y-axis direction, we have, again, equally spaced points. 0, 1, 2, 3, and so on, and -1, -2, -3, and so on in that direction. And then the convention is that if we have a point, like this one, called A, then we read off the x-coordinate, we read off the y-coordinate, and we put them together in what's called an ordered pair, okay, with brackets. There's the x-coordinate, which is 2, and the y-coordinate, which is 1. We put them together, and that's called the coordinate of A. And so we just write A equals 2, 1. Here's another point, the point 3, 3. 3 over in this direction, 3 up in this direction, and that's the point B. Okay, not only do we have points, but we also have vectors in this situation. So a vector is a directed line segment. It's a line segment with an arrow, with a direction. In this case, the line segment goes from A to B, and so we write V equals AB with this vector sign on top of it. Now I should point out sometimes people will write this in different ways. So sometimes people write AB with an arrow underneath there. Okay, that's just a matter of convention. And the separation between A and B is described by how far you go over in the x direction and how far you have to go up in the y direction. In this case, 1 over in the x direction and 2 up in the y direction. So this vector would be represented by the pair 1, 2. And I like to use round brackets for vectors to distinguish them from points with square brackets. So this is not a universal convention, but it's a very convenient one. And I might mention the most important point in this story is the place where the two axes meet. That's a special point called the origin. Its coordinates are, of course, 0, 0, and it's often denoted with the symbol capital O. That's the origin. So besides being able to describe points and vectors very efficiently, this setup allows us to describe lots of different objects. For example, lines. Here's an example of a line. And as Descartes realized, the line can be represented by an equation relating the x and the y coordinate of any point that lies on it. This line here happens to have equation y equals 2x plus 2. We say this is the Cartesian equation for this line. And we can check that, say, this point here, which has coordinates -1, 0, satisfies the equation. If you plug in x equals -1, then you get 0. And this point here, which has coordinates 0, 2, also satisfies the equation. This same line can also be described in terms of a parametric or vector equation. All right. This is a different way of describing the same line, and it says that the same line can be described by starting at the vector -1, 0. So here's the vector -1, 0. And then going some multiple, lambda, that's a Greek letter, lambda, times the vector 1, 2, the same vector that we had here. Okay. So the vector from here to here and the vector from here to here are the same. Same size and same orientation. And this equation represents the vector or parametric equation of this line. Finally, there are more complicated things that we can write out in this Cartesian framework. For example, here is a circle whose center is the point -1, -2, and whose radius is 1. And its equation is x plus 1 squared plus y plus 2 squared equals 1. So any point on here will have this property that it satisfies this equation. All right, so a very brief introduction to Cartesian geometry and some of the terminology involved there. Of course, geometry is a very, very big subject. There are many more terms and so on that are used, but these are sort of pretty fundamental ones. In our next video, we're going to have a look at some basic algebra and the language that we need to talk about first-year university mathematics. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.